You've always been told that the ultimate enemy in your fields is a single overwhelming fungal pathogen.
Yeah.
I mean, you see the damage, right? And you just assume there's this massive army attacking the roots.
Right. It's the logical conclusion.
Exactly. But what if the true cause of your biggest headache is actually, an inside job by the soil itself? Stick around, because the key takeaway on how to protect your palms comes near the end of this discussion. And honestly, it changes everything about how you'll manage your fields tomorrow.
Welcome to another podcast episode brought to you by AGS Agriculture Global Solutions, where we discuss sustainable oil palm cultivation topics.
It's really great to be here looking at this research with you today.
Yeah, glad to have you. Because for everyone listening out there, managing oil palm plantations day in and day out, we know your daily realities. We know the constant vigilance required to keep those palms healthy and, of course, keep your yield high in tons per hectare.
Oh, absolutely. Tons per hectare is, well, it's the ultimate metric, isn't it? It really is. So today we're pulling some insights from a really groundbreaking paper published in the IOP conference series, Earth and Environmental Science, and this is from the year 2026.
Yeah, a very recent, very illuminating study.
Totally. The mission today is to completely rethink basal stem rot, which we will refer to as BSR from here on out.
Right, BSR, much easier to say.
Exactly. We're taking this cutting-edge soil microbiome science-like, incredibly high-resolution DNA sequencing of the actual dirt beneath your boots, and we are translating it into practical, actionable steps.
And, that translation is just so critical because the conventional wisdom surrounding BSR it's basically been turned completely on its head by this data.
Okay, let's unpack this. When a farmer thinks about BSR, they're naturally thinking about the fungus Ganoderma bonus.
Yes, the classic villain of the story.
Right. And the historical assumption has always been a simple numbers game. The logic dictates that if you have a field heavily infected with BSR-like, the palms are yellowing, the lower fronds are collapsing, and you have those hard, woody, fruiting bodies popping up right on the lower trunks.
Which is an awful sight for any farmer.
It really is.
Yeah.
You see that, and you just assume the soil beneath those palms must be absolutely swarming with Ganoderma.
I mean, it makes complete intuitive sense, right? If you're looking at massive catastrophic damage above ground, you naturally assume there is a massive dominating presence of the pathogen below ground.
Exactly.
For decades, the agricultural community just accepted that endemic soils, which are soils where BSR is a constant, severe year-over-year problem, we just assumed they were practically overflowing with this specific fungus.
We treated it like a brute force invasion.
Yeah, exactly, a brute force invasion.
But this 2026 paper did something a little unusual. The researchers didn't just go in looking for Ganoderma. They took these deep core samples from completely healthy soils and then from highly endemic soils.
Right.
And they ran a full genetic census. Like, they sequenced the DNA of literally every microscopic organism living down there.
And the finding completely contradicts that whole invasion theory.
It's wild. In the soils where BSR was running absolutely rampant, Ganoderma accounted for only 2% of the total fungal population.
2%.
2%.
I mean, that is not an invading army. Ecologically speaking, that is barely a blip in the overall fungal community.
It's like assuming a bank robbery was committed by a massive invading army, but it turns out it was just one guy slipping in through the back door because the entire security system was already completely disabled.
That's a great way to put it.
But, how does that actually work in reality? If I'm a farmer staring at a massive, mature palm tree dying from BSR, it is incredibly hard to believe that a pathogen making up just 2% of the soil microbiome could take down a tree that size.
Well, what's fascinating here is that this research completely reorients how we view disease outbreaks.
How so?
The destruction of the palm isn't being driven by Ganoderma overpowering the root system by sheer biological mass.
Okay.
The pathogen is not a battering ram. What the data reveals is a deep systemic ecological imbalance. It's a collapse within the soil itself.
So the environment is already failing.
Exactly. The soil's natural defenses, its structural integrity, and the palm's inherent immunity have all failed simultaneously. And that multi-system collapse acts as a wide open door.
So that very small, highly opportunistic amount of Ganoderma can just walk right in.
Yes, it just walks in and initiates the infection.
So we really shouldn't be focusing on the 2%. We need to figure out why the security system failed in the first place.
Precisely. We have to look at the environment.
Let's dig into the mechanics of that collapse then. The researchers started by looking at the chemical foundation of the soil, right? Comparing the healthy areas to the diseased endemic areas.
Yes, and the differences in the chemical breakdown were frankly glaring.
What did they find?
Well, the endemic soils, the ones with the failing security systems, showed severe deficiencies across multiple critical metrics. First off, there was a significant drop in total nitrogen, or TN.
Which, I mean, makes sense as a stressor given nitrogen is the fundamental engine of vegetative growth.
Yeah,
But there was another metric that really stood out, right?
exactly. The carbon. The organic carbon, which we'll
Hmm.
call OC moving forward in the endemic soils, had plummeted to below 2%.
Wow, less than 2% OC. I mean, for any field advisor listening, you know that when your carbon drops that low, your soil is essentially running on fumes.
It really
But
is.
let's explain the why behind that. What does a drop in carbon actually do to the physical environment of the root zone?
Well, organic carbon is essentially the foundational building block of soil structure. It provides the energy source for the entire subterranean food web.
Right.
Without it, the soil literally loses its architecture. It becomes compacted, the water retention plummets, and, well, the environment just becomes incredibly hostile to the beneficial microbes that usually cycle nutrients to the palm roots.
And the chemical depletion didn't stop at carbon and nitrogen, did it?
No, it didn't. The endemic soils were also heavily depleted in specific micronutrients and macronutrients, most notably potassium, which we know as K, and boron, or B.
And this is where we see the direct link between soil chemistry and the palm's internal defense mechanisms.
Exactly. Let's look at potassium. In plantation management, we often think of potassium strictly in terms of yield, right?
Oh, totally. Applying K to maximize bunch weight and hit those targets in tons per hectare. It's usually just seen as the fruit swelling nutrient.
Right. But physiologically, potassium is absolutely critical for the plant's stress response and its inherent disease resistance.
Wait, really? How does it fight disease?
Well, potassium regulates the turgor pressure in the guard cells.
Hmm.
Those are the cells that control the opening and closing of the stomata on the leaves.
Okay, got it.
But it also acts as an essential catalyst. It drives the activation of over 80 different enzymes.
80.
Yeah, and many of those are responsible for synthesizing the defensive compounds the palm needs the second it detects a pathogen.
So if K is deficient,
If K is deficient, the palm's alarm system is practically muted. It just cannot manufacture its chemical defenses.
wow, here's where it gets really interesting. Because it means fertilizer isn't just about maximizing yield. It's literally the palm's immune system.
That is exactly right.
By the way, soil testing for acidity and nutrient content is essential. And remember to use leaf testing when relevant to get a complete picture of your palm's health. Because, you can't fix a failing chemical security system if you don't actually know which elements are depleted.
That monitoring is absolutely crucial because the chemical weakness of the palm is really only the first phase of the collapse.
There's more.
Oh, yeah. The physical armor is gone too. You mentioned boron earlier.
Right, boron, which is usually treated as an afterthought, like just a minor trace element. But the paper heavily highlights its absence in these endemic soils.
Yes, and to understand boron, you have to look at the microscopic structure of the palm's cell walls.
Okay, take us down to the microscopic level.
The cell wall is made of cellulose, right? But those cellulose fibers are held together by a complex matrix of a substance called pectin.
Okay.
Boron is the literal chemical tie that binds that pectin matrix together. It forms these borate esters that cross-link the pectin chains.
So it's like the rebar in a concrete wall.
Exactly like rebar. Now, think about Ganoderma. It attacks by secreting degradative enzymes, things like cellulases and pectinases, literally trying to dissolve the physical barriers of the root.
I see where this is going.
Right. If the palm is deficient in boron, that pectin matrix is not cross-linked. The cell walls are weak, they're brittle, and structurally compromised.
The physical armor is completely stripped away.
Entirely. When that fungal enzyme hits a boron-deficient root, the root tissue essentially just dissolves.
Which makes it incredibly easy for even a microscopic amount of Ganoderma to just push right through into the vascular system.
Exactly, and that's just the chemical and physical side. We haven't even touched the biology yet.
Right, because the soil isn't just a chemical reservoir. It's a living habitat.
Exactly. When those core nutrients drop, when the OC plummets below 2% and structural elements like boron disappear, the biological neighborhood around the roots fundamentally shifts.
So if the chemical foundation collapses, the ecosystem living on top of it collapses too. Let's talk about who actually survives in that wreckage. What happens to the soil microbiome when the carbon disappears?
Well, let's start with a healthy baseline. In the thriving soils they tested, the dominant fungi belonged to a phylum called Basidiomycota.
Gasidiomycota.
Yes, these are the foundational architects of the soil ecosystem. They are incredible decomposers, breaking down complex lignins, but more importantly, their fungal networks, the hyphae, literally wrap around soil particles.
Oh, with a net.
Exactly. They exude these sticky glycoproteins that bind the dirt into aggregates. They improve aeration, prevent erosion, and basically build a stable, healthy home for the roots.
Okay, but in the endemic soils.
In the endemic soils, those structural architects are entirely pushed out. The data showed the neighborhood gets taken over by a different group, opportunistic Ascomycota.
And the paper specifically pointed out one fungus, right?
Yes, they found a massive spike in a genus called Cedosporium.
Cedosporium. So the beneficial builders leave, and these highly tolerant, opportunistic scavengers move in.
Right. Cedosporium thrives in heavily degraded, nutrient-poor environments where, honestly, nothing else can survive.
Okay, hold on. Let's look at the actual diversity metrics in the paper for a second, because something doesn't quite make sense to me.
Sure.
The study measures alpha diversity.
Right.
It looks at richness, which is the total number of different species, and evenness, which is how equally those populations are distributed.
Correct.
If the endemic soil is dead, diseased, and lacking carbon, shouldn't the diversity numbers just be completely flatlining? How can a degraded soil have a higher evenness metric than a healthy, thriving soil?
It is a brilliant question because it does sound entirely counterintuitive at first glance.
Right.
Usually, high evenness indicates a perfectly balanced ecosystem, but you have to look at the context of the degradation. In a healthy soil, you have a distinct hierarchy.
Okay.
The highly specialized, beneficial Basidiomycota dominate the environment because they are actively managing the robust carbon cycle. They take up a large percentage of the population, which actually drives the mathematical evenness score down.
Even though the overall health and total species count, the richness is very high.
Exactly.
So healthy soil is like a bustling, diverse city with lots of different jobs being done. You have a massive population of specialized workers dominating the space,
Right.
surrounded by smaller niche communities.
Right. But in the diseased endemic soil, that entire complex hierarchy collapses. The dominant beneficial fungi are wiped out by the lack of carbon.
Leaving what?
What's left behind is a very uniform, evenly distributed layer of generalist scavengers. The higher evenness in the diseased soil doesn't represent balance.
It represents a ghost town, where only a uniform gang of tough, opportunistic scavengers can survive.
Yes, exactly. A completely flattened, homogeneous wasteland where only a few tough species scrape by in equal, desperate numbers.
Man, so the city is burned down, the specialists have fled, and you just have these scavengers picking through the rubble.
That's the reality of it.
But how does that specific environment actually benefit the Ganoderma? I mean, why does Cedosporium moving in mean the palm is about to get infected?
If we connect this to the bigger picture, opportunistic fungi like Cedosporium don't just passively exist in the rubble, they actively defend their new territory.
Oh, they fight back.
They do. They are known for immense metabolic versatility, and specifically, they produce fungistatic substances.
Fungistatic substances. Let's explain the mechanics of that.
Yeah.
Are they like actively attacking other microbes?
They are essentially poisoning the well. Fungistatic secondary metabolites are chemical compounds released directly into the rhizosphere, the root zone.
Okay.
These compounds can drastically alter the local micro-pH, or they can directly interact with the cell membranes of competing fungi, basically inhibiting their spores from ever germinating.
Wow. So the Cedosporium is creating a highly toxic, suppressed environment to ensure no other beneficial microbes can reestablish themselves.
Exactly. They want to keep all the tiny amounts of nutrients for themselves.
So they are actively terraforming the soil to keep it a wasteland.
Precisely. Now, bring Ganoderma back into the picture. Ganoderma is notoriously resilient.
Right.
So while the beneficial microbes are dying off from the lack of carbon and any new competitors are being actively suppressed by those fungistatic toxins, the Ganoderma is actually able to tolerate the toxicity.
Oh, I see. The opportunistic fungi have essentially cleared the entire biological battlefield for it.
You've got it.
Let's pull all of this together because the mechanics of this collapse are just staggering. The palm tree is internally weakened from potassium deficiency, meaning its stomata are compromised and it can't synthesize defense enzymes.
Right.
Its cellular walls are physically brittle and dissolving because there is no boron to cross-link the pectin.
Correct.
The protective beneficial microbes in the soil have starved to death from a lack of organic carbon.
Yes.
And the scavengers that took over are pumping out fungostatic toxins that prevent any biological reinforcements from arriving.
That is the exact sequence of the systemic failure.
So Ganoderma doesn't need to be this overwhelming army of 90%. It just waits until the palm is completely stripped of its internal armor, its physical walls, and its microscopic bodyguards.
Exactly.
Then, a tiny 2% population can easily bypass the broken security system, penetrate the root, and initiate a devastating BSR infection that eventually kills the palm.
It is a cascading failure of the ecosystem. The fungal fruiting body you eventually see on the trunk is just, well, it's the very final visible stage of a long, invisible systemic collapse.
So what does this all mean? As an agricultural field advisor speaking to farmers, we have to translate this complex microbiology and soil chemistry into morning instructions. The listeners need clear, actionable steps for tomorrow.
Absolutely.
How do we actually reverse a systemic collapse like this?
The first non-negotiable action for tomorrow morning is that you must aggressively focus on increasing soil organic matter.
Fixing that OC metric that dropped below 2%, right?
Yeah.
And the total nitrogen.
Yes. The mindset has to shift from purely chemical fertilizer application to deep organic matter integration. You need to utilize empty fruit bunches, heavily mulched prune fronds, or high-quality compost, and physically work it into the soil.
Because just adding synthetic MTK isn't enough anymore.
No, it's not. Because when you add organic matter, you are fundamentally altering the physics and chemistry of the root zone by improving the cation exchange capacity, or the CEC.
Let's explain the mechanics of CEC, because it's kind of the linchpin of everything we've discussed regarding the physical armor of the palm.
It really is. Cation exchange capacity is essentially a measure of the soil's ability to hold on to positively charged nutrient stations, like potassium ions and calcium ions.
Okay.
Clay particles and decomposed organic matter, specifically humic acids, carry a negative electrical charge.
Oh, so they act like magnets.
Exactly like microscopic magnets. When your soil has high organic matter, it has a high negative charge. It grabs onto the positively charged potassium and boron you apply as fertilizer, and it holds them tightly in the root zone so the palm can actually absorb them over time.
But in the endemic soils we talked about, the carbon was gone.
Which means the negative charge was gone. The soil loses its magnetic grip.
Wow.
You could pour hundreds of dollars of expensive potassium and boron onto that field, but the moment a heavy rain hits, those vital nutrients just leach straight down into the water table. The palm never gets the building blocks it needs to repair its pectin matrix or synthesize its enzymes.
So action 1 is restoring soil organic matter. By integrating empty fruit bunches, you rebuild the soil's magnetic sponge, the CEC.
Right.
That allows the soil to actually retain the boron and potassium, which allows the plant to rebuild its physical cell walls and tune its internal alarm system back on. You basically rebuild the physical biological armor.
That is step one. But, you cannot stop there, because chemistry is only half the battle.
Right. And here's where I want to push back a little.
Okay, go ahead.
Let's say I follow instruction 1. I add tons of empty fruit bunches, and I fix the CEC. The soil sponge is back.
Yeah.
But doesn't adding a massive influx of organic matter just create a really nice, comfy, carbon-rich home for the Ganoderma to multiply in?
It's a very valid concern.
Because if the soil is currently a toxic wasteland run by opportunists, how do we stop the pathogen from just taking advantage of the new food source?
That is exactly why Action 2 is critical, because the soil microbiome is currently out of balance and dominated by Cedosporium and other scavengers. You can't just throw food at the problem.
Right.
And you certainly cannot just pump broad-spectrum fungicides into the dirt. I mean, that will kill the Ganoderma, sure, but it will also kill whatever beneficials are left. And those highly tolerant opportunists, they'll just recolonize the empty space instantly.
So you can't just fight the pathogen.
No, you have to actively bring back the good neighbors. You have to repopulate the environment with biological reinforcements.
We have to bring back the specialized workers to drive out the scavengers.
Yes, you need to introduce antagonistic microbiota simultaneously with your organic matter. The 2026 research heavily supports the targeted introduction of beneficial fungi, specifically from the genus Trichoderma.
Trichoderma. Now, this is a name that gets thrown around a lot in sustainable agriculture literature. But in the context of a BSR-infected field, it has a very specific, aggressive job, doesn't it?
It does. It is not just a passive beneficial microbe. Trichoderma is a hyperparasite.
Oh, wow.
It basically engages in biological warfare. When you raise the organic matter, you create the hospitable, carbon-rich environment that Trichoderma needs to rapidly multiply.
Okay.
Once it's established in the root zone, it does two things. First, competitive exclusion. It grows incredibly fast, actively suppressing the spread of Ganoderma and outcompeting the Cetostorium for space and newly available
It
nutrients.
starves them out.
It starves them out, but it also actively hunts them. Trichoderma can detect the chemical signals of pathogenic fungi.
Wait, really? It hunts them down?
It literally will physically grow toward the Ganoderma, coil its hyphae tightly around the pathogen, and secrete powerful enzymes, chitinases, that literally dissolve the Ganoderma's cellular structure.
That is incredible. So while boron is building up the palm's walls on the inside, trichoderma is actively dissolving the enemy's walls on the outside.
Exactly. It forms an aggressive biological shield around the palm's roots, ensuring that the marginalized 2% Ganoderma population stays marginalized or is eradicated entirely.
This represents a total operational paradigm shift for any advisor or farmer managing these lands. Managing BSR isn't about finding a more toxic weapon to eradicate a massive, unseen fungal army.
Not at all.
It's about recognizing that a diseased palm is the symptom of a dead soil ecosystem. You cannot protect the tree if the ground it stands in is chemically depleted and biologically toxic.
You must treat the root cause, not the final symptom. If you stop the ecological collapse, you stop the disease.
So you rebuild the physical armor by restoring the CEC, so potassium and boron can do their jobs, and you hire microscopic bodyguards by inoculating with trichoderma.
That's the formula.
This has been an incredibly rigorous look at the unseen mechanics beneath the plantations. We started with the terrifying image of an unstoppable fungal invasion, only to realize the real vulnerability was the collapse of our own soil's architecture.
This raises an important question, I think, for everyone listening who manages commercial agriculture. What if the future of suppressing devastating crop diseases isn't found in engineering a new, highly toxic chemical fungicide, but simply in learning how to effectively farm the complex, invisible, microscopic ecosystem beneath your boots?
That is a powerful framework to keep in mind as you head out to survey your fields and assess your soil health tomorrow. Look at the dirt. Remember the chemistry and the biology interacting just below the surface, and realize how much life is waiting to be properly managed down there. Thanks for listening.